Hi, in this lesson we are going to learn about some special angles and their properties so that we can figure out sine, cos, and tangent ratios without the need of a calculator. There are three groupings that I'm going to go over. The first one are called quadrantal angles. Now, quadrantal angles are angles that are right on the axes. So for a standard position point of radius r, first of all, let's mark off some coordinates. This would be r comma 0. This place here would be 0 comma r. Over here, negative r, 0. And down here, 0, negative r. Now, recall, we've talked about the sine of the angle being y over r, and cos of an angle being the x-coordinate over r, and the tangent of the angle being y over x. With that in mind, I'd like you to write an expression for the sine of 0 degrees. Okay, if you've thought about it for a moment, pause if you need to. Now, the y value at 0 degrees is 0 over r. So the sine of 0 is the ratio 0. The cos of 0 is going to be the x-coordinate over r. So whatever the r is, it's r divided by itself, or 1. For this lesson, I'm not going to, should I do tangent? Yeah, I'll do tangent, sure. Tangent of 0. Well, the y-coordinate is 0, the x-coordinate is r, so the tangent is 0. Okay, I'd like you to do the same thing now for sine, cos, and tan of 90 degrees, and pause and then rejoin me. All right, sine of 90 is r over r, so 1, similar to what happened with cos of 0. The cos of 90 is 0 over r, like the sine of 0. It's 0. And tangent is r divided by 0, and you'll recall that when something is divided by 0, we get a number undefined in the real number spectrum, or just undefined. All right, I'd like you now to try doing 180 degrees over here, and 270 degrees. Finish all of those off, and then check your work against mine. Okay, here are the rest of your answers. The explanations are similar to before. Check the coordinates, check the values. Hopefully that all makes sense based on the definitions. So that's the first type, quadrantal angles, angles right on the axes. Here's the second type of special angle, 30 and 60 degree angles. And I'm going to build this up in case you don't remember or haven't seen it before. I'm going to make an altitude from A to D. Altitudes meet at 90 degrees. I'm going to start with a triangle that's equilateral. That means all the sides are the same. Now I'm going to arbitrarily choose the sides to be 2. It's convenient for me. Equilateral triangles have angles of 60. And this altitude will create two triangles that are completely congruent with each other. They have sides that are shared, another side, right angles, and the third side, or pardon me, a second angle, and therefore third angles would be equal. And so by several methods, these triangles are completely congruent, leading to this having a side of 1 and this having a side of 1, since the entire thing is 2. Now, from that, I'm able to figure out how long AD is. I have a right triangle with hypotenuse and side, so I take 2 squared minus 1 squared and root it, and I'll find that my altitude is root 3. So, what we have is essentially a triangle with a 60 degree angle. That's a very poorly drawn triangle. Let me try that again. A triangle with a 60 degree angle and a 30 degree angle, and a 90 of course, and a known ratio of sides. Now from that, I can figure out the sine of 30, the cos of 30, the tan of 30, and as well for 60 degree angle. So I'd like you to do that right now. Write down your predictions of what the sine, cos, and tangent of 30 and 60 degrees are, and then check your work against mine. Okay, here they are. Now, I've left these with exact value radicals. Root 3 can't be evaluated. It can only be estimated with a calculator as a decimal, and that's not better. Leave these in exact form. Radicals like this are referred to as exact value answers, okay? We don't need a calculator to work these out. They're all based on definitions. Notice a couple of symmetry patterns here, that the sine of 30 degrees as a ratio matches the cosine of 60 degrees as a ratio. Same with the sine 60 and cos 30. And another interesting pattern, that the tan of 30 and the tan of 60 are reciprocal relationships for ratios. And I'd like you to think about why that is. There is a logical explanation if you study the diagrams. Okay, now remember from previously that we talked a bit about symmetry in the different quadrants in standard position. If this was 30 degrees, this angle over here is also a 30-degree reference angle, but in standard position this would be 210 degrees. Likewise, if I sketch some 30-degree reference angles for quadrants 2 and 4, what we'll see is that the imaginary little right triangles in each of the 4 quadrants, based on the 30-degree reference angles, are going to cause relationships of the sides that are identical. These triangles are all congruent. If the radius were 2, the y value would be 1. Y value over here would also be 1. Y value here would be negative 1. And the y value here would be negative 1. All radii are equal to 2. And so, knowing this relationship about sine of 30 degrees being 1 over 2 will help me know what the sine of the reference angle in quadrant 2 is, or sine of 150. So the sine of 150 is also going to be 1 over 2, based on corresponding triangles. And the sine of 210, well, you think of what that is. I'll give you a moment. It's also going to be a ratio of 1 over 2, because the reference angle is the same. But now I'm in quadrant 3, so it's a negative ratio. And try this one. The sine of 330 degrees, over here, reference 30, that ratio will be negative 1 over 2 as well. All right, so once I know about 30-degree reference angle and the ratio of 1 to 2 for sine, I automatically know about sine 150, 210, and 330 in standard position. All I need to consider is what quadrant, and do I make a plus or a minus sign, which we talked about in the previous video. Based on that, I can do the same thing for cosine 30 degrees as well as 150, 210, 330, and the sine and the cosines of 60 and their corresponding standard position angles in the other quadrants. So all of these now become apparent and evident to us, hopefully. If I'm working with sine 60, I'm going to be also thinking about the sine of 120, the sine of 240, and the sine of 300. Now, I'm going to leave this with you to figure out what those ratios would be and what their sines would be, and then check it on your calculator to verify it. The same idea holds true for the cosines and for the tangents of all of these 30 and 60 degree angles put in any of the 4 quadrants. So the family, I sometimes refer to these as families of angles. The 30-degree angle, the 150, the 210, and the 330 behave in a similar way. The 60-degree angle, the 120, the 240, and the 300, again, behave in a similar way. All right, we've got one more special angle to learn about, and that is the 45, 45, and 90 degree in an isosceles right triangle. Now I'm going to arbitrarily choose those sides to be 1 because that's convenient and easy. Pythagorean theorem would tell me that that's root 2. Because I have a 45-degree angle, I can now figure out the sine, cos, and tangent of 45 degrees. You should pause and figure these out, and then rejoin and check your work against mine. Here you go. 1 over root 2 can also be written, by the way, as root 2 over 2 by rationalizing. Either form, they're equivalent, they're both good. Same for the cosine. Tangent is 1 to 1, or 1 result. And like I talked about previously, now that I know about the behavior of a 45-degree angle in quadrant 1, I'm going to be able to extend that knowledge into quadrants 2, 3, and 4 with reference angles of 45. So this family of angles that will behave similarly are 45 degree in quadrant 1. Why don't you figure out the other 3 and then unpause the video. There you are. 180 minus 45, 180 plus 45, and 360 minus 45. All of these angles are going to exhibit these ratios, and all you'll need to consider is a plus or a minus sign on that afterwards. Okay, I'd quickly like to look at a couple of examples that use this now. and I'm kind of getting late on this video, so I'm going to keep this fairly brief. Find exact values without calculator. So in 1, I'd like you to figure out the sine of 300 degrees, or A I should call it, I guess, and B, the cos of 225. Ask yourself, what's the reference angle? What's the quadrant? What's the ratio? What's the sine that you would know, and therefore the answer? Try that for both of these, then rejoin me. Alright, I did the first one. I thought it might be difficult for you, so I'm just going to do this first one and then talk it out. 300 degrees is in quadrant 4, and a reference angle of 60 degrees. I need 60 degrees more to get to 360. The sine of 60 degrees matches the ratio of root 3 over 2. In quadrant 4, sine is negative because it's y over r. Therefore, the answer is negative root 3 over 2 as a ratio. Try doing the same thing with this one. Similarly to before, 225 is a little more than 180. It's 45 more, so the reference is 45. I'm in quadrant 3 as a result. 45 degrees with cosine matches the ratio of 1 over root 2, or root 2 over 2. Quadrant 3 for cosine means the x is negative, so the sine will be negative, and your answer is negative 1 over root 2. This is the basic idea of how to work with these problems. Other problems that you can be asked for that are similar to this could be working the problem backwards, such as this. Solve for an angle between 0 and 360 degrees when you're told the sine of the angle is negative 1/2. It's very similar thinking, but we have to back some things up and do it in reverse order. This ratio with sine corresponds to a reference angle of 30 degrees. This sine tells me that I'm in quadrant 3 or 4 for a sine function. A 30-degree angle in quadrant 3 is 210 degrees, so that's one answer. A 30-degree angle in quadrant 4 is 330 degrees, so there are two answers to this equation in standard position. That's it for this lesson.